Hey friends, this is Kruti Jaipancholi, Assistant Professor in LJ Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject fiber optic communication. So friends, till now we learn about the structure of the fiber as well as the degradation in the fiber. So now the sources which are required to convert your electrical signal into the optical form so that it can travel through the optical fiber. So now we are going to start our journey in some other direction, that is the optical sources and coupling. Now as we know that from this video you will learn about the light source materials and related examples. Now the light sources, which are the LED and the laser, which are the material which required to make this kind of the light sources. So the spontaneous emission due to the carrier recombination, which is known as the electroluminescence. To encourage the electroluminescence, it is necessary to select as appropriate semiconductor material, because these are the diodes which are made up of the semiconductor material, and that depends on the energy band gap, and which can be categorized according to that band gap energy, and that are the direct band gap semiconductor and indirect band gap semiconductor. Now about this band gap semiconductor, we have a table which gives us the idea about the various semiconductor material, the energy band gap, that is in the EV, and the recombination. Okay, so now the various material for that, the GaAs, GaSb, InAs, InSb, silicon, germanium, Si, Ge, GaP. Okay, so these are the various material that can be used to fabricate the various light source. Okay, that are the LED or the laser light. The energy band gap, that is shown over here. That is the direct band gap or the indirect band gap. What is the direct band gap? In the semiconductors, the electrons and holes on the either side of the band gap that have the same value of the crystal momentum, as well as the direct recombination that is possible due to that. And this recombination that will occur within the 10 raised to minus 8 to 10 raised to minus 10 second. The other thing that is with the indirect band gap semiconductor, the maximum and the minimum energies that occur at the different values of crystal momentum, and this recombination that is in this semiconductors, that is quite slow, and would be around 10 raised to minus 2 and 10 raised to minus 10 second. So this is the direct band gap and the indirect band gap. In the direct band gap, the semiconductor electrons and the holes that can recombine directly without the need of third particle to conserve the momentum. And in these materials, the optical radiation that is sufficiently high. These materials are the compound of the group 3 elements, which are the Al, Ga, In, and the group 5 elements, that are the Pa, As, and Xb. Some tertiary alloys, that is the Ga 1 minus X, Alx, are also used. This 1 minus X that are known as the mole fraction. Mean the Ga1 minus X AlX, that is the alloy, and in that the Ga material, some impurities that can be added to achieve the actual characteristics. So these are referred to as a mole fraction. Now the emission spectrum of Ga1 minus X, AlX, AS, LED, that is shown in this diagram. So here this is of the wavelength, and on the y-axis there is the output power. So here we can say that the value, this emission spectrum, that is what? So the peak power, that is at the 810 nanometer, and for the X value is equal to 0.08, the ratio of the aluminium, and the gallium arsenide, so that we can found over here. So this way we can have the highest intensity, highest power which we will get, at this particular wavelength. So this is the specifically for this material. If you will select the other material, you will get the output power at some different wavelength. So the peak output from the direct diagram, the peak output power, that is Optic, at 810 nanometer. The width of the emission spectrum at half power is referred to as a full width, half maximum spectral width. And for that diagram, this for given already FWHM, full width half maximum, that is the 36 nanometer. So the fundamental, the quantum mechanical relationship which will be between the gap energy E and frequency V is E is equal to H into V. So you can write the E is equal to H into C upon lambda. So lambda is equal to HC upon E, and here energy E is in joules and wavelength lambda, that is in the nanometer. Expressing the gap energy Eg in the electron volt and the wavelength in micrometer for this application, and this lambda micrometer is equal to 1.24 upon Eg, and that is in the EV, that is the unit. So different materials and the alloys have a different band gap energy, and the band gap energy that can be controlled by two compositional parameters, X and Y, within the direct band gap region. So within the direct band gap region, the quaternary alloy, that is IN 1 minus X, GAX, ASY, P1 minus Y, in the principal material suited in the such LEDs. So two expression relating EG and XY, that are EG is equal to 1.424 plus 1.266x plus 0.266x square. So this is the equation for the band gap energy. Now using this, we will solve the examples. Compute the emitted wavelength from an optical source having a x is equal to 0.07. Now, here the equation is given to us, that is x is equal to 0.07. We have derived the equation, So this equation, that is for the band gap energy, and it is the Eg is equal to 1.424. Put the value of the x over here. So by putting the value of the x, we can determine the value of the Eg, that is 1.513 eV. So now We know the equation, that is the lambda. Lambda is equal to 1.24 upon Eg. Lambda is equal to 1.24 upon value of the Eg, that is 1.513. So lambda is equal to 0.819 micrometer. Now we'll solve the example. Second example. For an alloy Ln 0.74, Ga 0.26, As 0.57, P 0.43 to be stored in a array. Find the wavelength emitted by the source. Now here you have seen that the alloy of this material, how the X and Y that are there with that. So we have to consider that alloy to make this alloy, this array. So now we'll solve the example. That is, comparing the alloy with the quaternary alloy composition, which we have seen earlier. So it is here the IN, the 0.74, GA 0.26, AS 0.57, P 0.43. So it is found that the value of the X, that is 0.26, and Y value is 0.57. Now the ready-made equation that is available with us. So it is the Eg is equal to 1.35 minus 0.72y plus 0.12y square. So now by using this relationship, 1.35 minus in bracket 0.72 multiplied by 0.57 plus 0.12 multiplied by 0.57 square. So it is Eg is equal to 0.978 eV. So this is about, okay, this bandgap energy. Now lambda is 1.24 upon Eg. So we'll put that value in the equation. So lambda is equal to 1.24 upon 0.978. So lambda value is 1.2671 micrometer, and it is the lambda is equal to 1.27 micrometer. So this is about the example related to the light source material. So thank you very much everyone.